But here is this gigantic, and you could have just copied and paste and do that in the Mathematica. And the number one is that find this maximal exponent. I gave you the eigenvalues, right? So here's what I did. I use the Mathematica, just keep changing this power and compute the dimension. T minus 0i, right? So it's just t. Dimension is 2. Next one was a dimension 4. Bumped it up, dimension 4, and dimension 3. Third power is dimension 5. Go all the way to dimension 6. So once you hit the dimension power 4, and all after that, it doesn't change. It remains dimension 6 all the time. Does that make sense? So the answer is L equals 4. That's maximal exponent that it doesn't increase that space anymore. And that showed up as the minimal operator part. This L equals 4 is the part in the minimal operator. To do the same thing, t minus 32i, that's the eigenspace, right? Dimension 2, you push it one more. It's like pulling it back like a Jordan chain, but we're not doing the Jordan chain with the one element. We're doing just everything all together. Everything must be in here if it is associated with the eigenvalue 32. Dimension 3, 2 to 3. The next one picked up another dimension 4, and and no more. So m equals 3. Third time it picked up the maximum possibility. So that was part A. You're supposed to discover that in the part A. Compute the maximal exponents L and M such that this thing does not become any larger. And we talked about it briefly in class. Part B is showing this structure. And I explained it in class. It goes like this. All right, this is all you're going to get. If you just increase this power, you're not going to get anything. The maximum power is 4. It's discovered. Now you strip it off. Let's look at the maximum power of 3, and there must be something more, right? Existence is obvious. This is a subspace of that. Therefore, there's always a base extension theorem. Remember that part? Base extension theorem. There is this thing here, existence. Next one, I put a little bit of condition. When you strip off this one, third power, we want to keep this. We want to create a Jordan chain. So if you hit this one with that t minus lambda, it go inside there. So I want to keep that. If you hit u4 with a t, then it goes inside a u3 that we want to discover. So I call it u3 prime. And this was injective. Can somebody explain why this one, if you hit t with u4, it goes inside to the next level, but injectively? Can somebody explain why it's injective? If you're like, you're peeling it off at the end. So u4 is guaranteed that it does not have a kernel of t. Therefore, it injects in there. So if it is dimension 5, this 5 will show up exactly in the next level. It might have more, so that's why we have to extend it here. Let's look at the fact. Here's dimension 6, all the way right. What was the next level dimension? 5. So what would you say about dimension of u4? This guy dimension 5 and this guy dimension 6. Dimension 1, right? So if you push it inside in there, that's going to be just dimension 1 survive. But what is the next one? You have to keep calculating. So keep repeating this procedure. Push it to the next level, extend it so that it makes a right complementary problem, and push it further, and that's the structure of this one. UL goes to UL minus 1. You push it one more t, UL minus 2, and all the way down to U1. These are all the eigenvectors. If you do that, it naturally generates Jordan chain. Does that make sense? Because UL goes inside the next component, fit right in, and that creates a chain right there. It is about proving the existence of this one. Okay? And next part, I asked you to actually discover those things in actual vectors. So here is the key part. UT4 has all the way out there U4, right? But up to here was a dimension 5. So I conclude this is dimension. Well, I realize going from the bottom is easier. Here's kernel is a dimension 2, right? When you go to next level, how many more dimensions you pick up? 2 more dimension, right? And you pick up 1 more dimension and 1 more dimension. That gives you the clear idea about what are these component's dimension is. Is that clear? So I counted that two more dimension, one more dimension, and one more dimension. So that's the structure. And we know the existence of this one looks like this one more dimension actually go right into that. That's how we choose this U3. Dimension theory says however you choose it, the dimension is going to be same. So I don't have to pick up another one. It's the right size, right? One dimension go exactly one dimension. But this one dimension goes inside one dimension, but there's more. So you have to discover that. And then you have two vectors now, pushes it. So chain looks like this. All the way there's one vector. If you push it, it creates this chain. And if at level 2, it discovers one more and pushes one more. So what is the dimension of this nullity 4? Altogether 1, 2, 3, 4, 5, 6. The dimension 6 is chain structures like this. And you do the same thing, discover 2, 1, 1. If you think about chain structure, this is the only chain structure, right? From here, Jordan canonical form is computed already, right? Just with this much information, you already know how the Jordan canonical form looks like. This is one Jordan block, that's one Jordan block with the eigenvalue 0. Here's one Jordan block with eigenvalue 32. This one Jordan block with eigenvalue 32. So you can write that down. But the usual thing I do, and I ask you more, then I want you to actually calculate these vectors, right? So I have to go find actual this vector and push it, and I have to discover that vector and push it. And for that, I'm going to skip that, but I had to use a lot of echelon form to figure out which one is linearly independent. That is a very inefficient process. Only you can do that efficiently. Think about it, you have 20 vectors, and how are you going to sort it out which one is linearly independent, dependent? Row echelon form is the best way to do it. So by doing that, you can, if you're interested in, read it. So I sorted out, that's our Q4. Q4 is this guy. So I figured it out. All right, here's a Q4. Where is it? Yeah, that was a Q4. So this is null space of a dimension T3. And I hit it mathematically, or you compute this matrix, you hit it with a calculator, and that gives you 5 vectors. If you hit it with that, it gives you 6 vectors. You want to figure out which one among here is really belong to U4. Right? This is too big. You just can't calculate that U4 directly. So I compare them. And then echelon form says this one here is not belonging to null T3. So I take that, push it all the way down. So these are the vectors. And at the second stage here, and you have to do it again, there is a second stage that doesn't belong to whatever that you're comparing with. Q2 is coming from earlier chain. So I figure out there is this vector, and I push it one time. These 6 vectors gives you this chain right here. Okay, and you do exactly the same thing to get this 3 chain and 1 chain. And of course, the Jordan canonical form, because of that, looks like this. From here, you know how the minimal operator looks like, things like that. When you first learn this eigenvector structure and diagonalization in first year linear algebra, I think you hang on to something called characteristic polynomial. Remember that? Characteristic polynomial. Now you know the characteristic polynomial is not really telling you the full story. And I'm telling you actually minimal polynomial captures better, right? But because of this, minimal polynomial doesn't say how these two factors are mingled together. It's just all same minimal polynomial. So what is the real picture? The full information. Isn't that this guy? This is the full information. Dimension of that, dimension of the next level, dimension of the next level. If you have a sequence of this number, that tells you everything about the structure of the map you're looking at. So this is the full answer, actually. That is the complete discussion on Jordan canonical form in terms of computation. Any question? Some of you were close in discovering this one.